For the introduction, massive multiple input multiple output system that provide a high degree of freedom for radio channels have emerged to meet the increasing demand for high data rate transmission in fifth-generation cellular networks. A massive MIMO in a single-cell massive MIMO system provides a flexible platform to enhance network capacity and reliability and maximize energy efficiency. Ensuring the availability of 5G communication technology is important to multimedia service providers, as the quality of video traffic, digital video broadcasting, and online video stream is important to facilitate large-scale distribution and demand for high-rate data transmission, which requires a reduction in energy consumption. For the background, the aims to provide a solution to control power allocation problem identified as an essential metric in a massive MIMO system that maximizes energy efficiency. It also to maximize the non-convex IEE in a downlink massive MIMO system using a proposed energy efficient low complexity algorithm that guarantees optimal power allocation solution based on Newton's method and joint users allocation based on the range decomposition method.
Several issues that have been raised in the journal is: first, the authors address the problem of energy efficient power allocation using a specific low complexity algorithm to maximize EE. Second is the authors also propose a single low noise amplifier in the uplink to reduce cost and power consumption to maximize EE. Third is power allocation in the DL single cell massive MIMO system by increasing the number of transmitting antenna, arrays, and number of users to increase network capacity and reduce power consumption. Fourth is to improve EE while achieving high spectral efficiency in massive MIMO system by using a power amplifier and a power allocation algorithm based on zero forcing. Fifth is to maximize EE in massive MIMO using enable AF multi-way relay network. And sixth, to use a single antenna per user for point-to-point radio recognition. Seven is to investigate power allocation optimization in downlink by calculating the total rate for all users based on actual power consumption model. Last but not least is to use an iterative numerical algorithm to maximize EE in a point-to-point MIMO system.
I'm going to talk about the goal of this study paper. The objective of this study paper is to provide a solution to control power allocations problems identified as an essential metric in a massive multiple input, multiple output system that maximize energy efficiency. And the second objective of this paper is to maximize the non-convex energy efficiency in a downlink massive multiple input, multiple output system using a proposed energy efficient low capacity algorithms that guarantees optimal power allocation solution based on Newton's method and joint users association based on the Lagrange decomposition method.
Hi, I'm recording now. I present about methodology. There are 5 system modules in this paper, which to maximize the non-convex energy efficiency in a downlink massive MIMO system. For the first system model is the receive signal model, because this paper is focused on the transmit power allocation and user association in the downlink, and the base station equipped with large number of antenna M that are the active users are scheduled at the same time frequency resources, and the complexity overhead scheme provides the nearly optimal rates, and besides the perfect CSI is assumed to available the base station to generate the correlation channels and height channels gains for different users as height dimension channel vectors. Okay, for the second one is the energy efficiency formulation in massive MIMO system. The EELCA maximize the EE depends on the optimizing the objective function over all transmit power allocations, and the power control is essential to improve system performance by optimize high achievable data rate and energy efficiency. To minimize the active user, the transmit powers the total power consumption model for downlink is adopted. So with this formula, which is a quasi-concave function, confirm that exists a unique global optimal transmit power allocations. Okay. The third one is the constraints energy efficiency for power allocation and joint user associations. The energy efficiency is a formulate in the key optimizations problem under the overall transmit power and minimal data rate constraint, and the paper has described the optimization problem by using calculation, and to solve the original optimization problem, a two-step solution which consists of both power allocation sub-problem and user association sub-problem is proposed. The fourth one is constraint energy efficiency for power allocation scheme, which optimization problem proved that the energy efficiency is still quasi-concave when the total transmit is used for the circuit power consumption. So to solve this problem, the study have used the Newton method to solve the optimization problem. Okay. The next one is the constraints joint user. The efficiency of energy efficiency depends on studying the power allocation and joint user association based on EELCA. The problem of joint user association as an optimization problem which maximizes the energy efficiency of the base station under the transmit power constraint of the base station and the minimum rate constraint of the user equipment is formulated. Okay, the last one is the unconstrained energy efficiency power allocation. The unconstrained problem can be solved by proposing the exact solution to obtain the unconstrained non-convex optimization problem used to select the optimal power allocation for each n channels to maximize the energy.
I will discuss about the result and discussion. This section discuss the EE performance with power allocation. The number of Monte Carlo simulation was set to 10,000 using MATLAB, which is, as you guys can see, table 1, parameter and value. They are all given the value. The one is a constraint energy efficiency. Okay, figure 1 show the EE versus the maximum transmitted power for different value of PC. The purpose low complexity algorithm increase EE with total transmitted power allocation PT. Okay, as you guys can see, the red one is PC 400 milliwatt and M200, and the red one is 800 milliwatt and same value for M200. Also, the blue one is 1200 milliwatt and same value for M200, which is this transmitted power for dBm, and this one for y-axis is EE in millibit joule. Okay, the graph shows that the optimal EE can be achieved based on the optimal transmit power. Massive MIMO system with M equal to 200 transmit antenna and PC 400 megawatt. From figure 1, when the maximum EE 4 equal to 4.4 megabytes and the transmitted power equal to 10 dBm with PC M equal to 400 milliwatt equal to 200. EE starts increasing and giving the maximum value of EE, which is 3 megabit per joule, when the transmit power equal to 25 dB net consumption circuit power PC, which is 100 milliwatt. And this one is the figure 2 result for figure 2. Figure 2 show that the EE start increasing based on the total power and is sufficient, which required the minimum rate Rmin. After that, the EE start decreasing depending on serving several distributed user and sufficient transmitted power for every user, which is the times k. The figure 2, when the number of user which is k equal to 15 and lambda equal to 600 milliwatt, the maximum is EE equal to 7.2 megabyte which is per joule, and the achievable data rate Rmin equal to 2 bit per second. The EE decrease quickly with increasing data rate because more power is allocated to user with back channel according to channel 1. And transmitting power data to every user depend on high channel gain, which is the EE decreases with an increase in data rate requirement. Okay, next. Figure 2 also show the results that the EE start increasing based on the total power and minimum Rmin after reaching maximum. The EE begins to decrease due to an increase in the number of RF chains and the large number of distributed user. The EE start decreasing and becomes saturated depending on the number of distributed user and sufficient transmitted power to every user. Okay, and this one is the figure 3, which is figure 3 show the EE in the purpose EELCA increase when the number of user is small. When the number of users is large, the EE becomes slower. When the number of users continues to increase, the EE start to decrease because of the trade-off between data transmission and power consumption. Due to the high loss caused by the distance between BS and UES, the transmitted power will increase, which decrease the EE. Also, figure 3 show that there is an optimal number of users resulting in maximum EE for different number of antenna. And the last one is the maximum EE equal to 5.9 megabyte and per joule when the number of distributed user K equal to 33 with PCM equal to 100 milliwatt, which is 200. However, when the number of antenna is small, PCM equal to 1000 milliwatt, which is 100, the number of distributed user K equal to 30 and the maximum is equal to 55.4 megabyte per joule. Moreover, when the number of antennas decrease to PCM equal to 1000 milliwatt, which is 50, the distributed user K equal to 28 and the maximum EE equal to 4.5 megabit per joule. Okay, the purpose low complexity algorithm aims to provide maximum EE depending on the movement of several users related to a specific number of antenna. Okay, next. And this one is a result for figure 4. Figure 4 show that transmitted power allocation for user versus circuit power consumption, where the circuit power value started from 0 dBm to 70 dBm. The figure show that transmitted power for user increased by slowly when the consumption circuit power was low because more antenna were used to specify the minimum data rate requirement. The proposed EELCA was used to decrease the number of activated antenna and satisfy the transmitted power requirement to save energy when the maximum transmitted power for user is increased. And figure 4, when the circuit power was high, the transmitted power for user become constant because of the amplifier efficiency for every antenna that accounted for the power dissipation in the amplifier, which is dependent on the hardware quality employed at the BF. In addition, the circuit power consumption increased linearly because the power cost of RF change with increasing antenna. Okay, for the result for B, unconstrained energy efficiency result. In order to characterize the proposed EE power allocation, the EELCA is computed when more antenna are equipped with a number of antenna based on available channel gains. Okay, this one for figure 5, number of antenna and energy efficiency. Figure 5 show the relation between the EE corresponding to the number of transmitting antenna with different RF chain circuit and the proposed low complexity algorithm. However, this EE start to decrease when the number of antenna become larger only when circuit power consumption is considered. Looking at the number of RF chain for the activated antenna, the EE start to increase and decrease when the number of antenna increase due to increased power consumption and RF chain start to impact on EE. And figure 5 show that energy efficiency low complexity algorithm, the maximum EE equal to 7.2, 6.8, 6.5 megabyte per joule. The number of transmission antenna M equal to 200 with K equal to 16 and 8 and 4. When the circuit power PC 400 milliwatt, EE becomes constant as the power dissipates because of the amplifier efficiency for every antenna. The performance of the proposed power allocation algorithm in terms of EE is start increasing to a maximum value EE based on the number of antenna 200 when the number of distributed UE 20, 10 and 5 and the total transmitted power equal to 0.01 milliwatt. And the last one is a figure 6 result for figure 6. The optimal transmitted power value for user K is directly estimated using the available channel gain with the requirement of the transmitted power allocated to other equivalent channel. The figure shows that the total transmitted power decreased with increasing number of antenna in a single cell, where the power consumption increased because of RF chains consume a lot of power at the BF. Also, the figures show that the total transmitted power increased when more distributed user and total transmitted power increased faster than linearly with a distributed number of user and reduced linearly with an increasing number of antenna. The range of total transmitted power value was 90.2 minus to 11.2 watt with 20 bs antenna that decreased radically to 4 minus 2 with 200 bs antenna because of large RF chain loss, and based on the distributed number of user K, 68 and 4 respectively. The proposed EELCA provides more transmitted power when the number of distributed users is large. When the number of users is small, the total transmitted power decreases because of a small RF chain loss.
And as the conclusion, the problem solve the problem associated with the power allocation and the joint user association for a DL single cell massive multiple input MIMO system to optimum EE based on Newton method. Using ELCA, EE was maximized with the maximum transmit power and minimal data rate will constraint. The unconstrained EE was obtained by finding the root of the first derivative of the EE based on differentiating the instantaneous power allocation. And as the solution, by using the ALCA, the recommended in this research which maximize the DLEE under the explicit power allocation joint user association and constrained with perfect channel estimation. And as the result, the simulation result produced a maximum EE, transmit high amount of the coupled with the large RF chain loss, which increased circuit power consumption cost. When the result compared with the other research, show the ELCA maximized EE with transmission across a number of antenna. Other function of ELCA using to get the number of activated antenna to specify the transmitted power requirement to save the energy when the user need more power.